Hello everyone! Today, we're going to discuss a truly baffling mystery that made waves in the field of astrophysics in 2023. This is the kind of enigma that had physicists scratching their heads, struggling to make sense of it, because it seems so unusual and unlike anything we had encountered before. The event we're referring to is officially known as KM323-0213A, and it was detected by the KM3 net, a massive underwater neutrino detection network situated near the coast of Italy, on February 13, 2023. The KM3 net captured something that left the scientific community stunned. A neutrino particle so powerful that it completely shattered previous records for energetic neutrinos. To give you some context, neutrinos are incredibly elusive particles, and even though we've been detecting them for a while, this particular neutrino was so powerful that it made no sense at all when compared to previous data. To fully appreciate why this discovery was so remarkable, let's first explore some basic concepts. Neutrinos are elementary particles that have no electric charge and an incredibly tiny mass, though exactly how tiny, we still don't know. What makes neutrinos so mysterious and difficult to understand is their incredibly weak interaction with matter. In fact, trillions of neutrinos are passing through your body every second as you read this, and you don't feel a thing. This is because neutrinos interact with matter through what is known as the weak force, which makes them extremely hard to detect. This is why scientists have developed massive neutrino detectors like the IceCube Neutrino Observatory in Antarctica, which uses huge arrays of detectors to capture neutrinos when they do interact with matter. More recently, another neutrino detector called KM3 Cubic Kilometer Neutrino Telescope was created in Europe. Located underwater off the coast of Sicily, this detector works on a simple but highly effective principle. When neutrinos interact with matter, they often produce other particles like muons. Muons are relatively well known to scientists and are much easier to detect because, unlike neutrinos, they interact strongly with other matter and produce visible light as they do so. When a neutrino produces a muon, the muon travels through the water, emitting a burst of light, which is what researchers refer to as Cherenkov radiation. The more powerful the neutrino, the more powerful the muon, and the brighter the burst of light it produces. On February 13, 2023, something extraordinary happened. The KM3 detector, with its 21 detection units, registered an incredibly high intensity of light. Within a mere 2 microseconds, 28,000 photons were detected, which was so much light that it saturated 25% of the detectors, essentially blinding them for a short period. To understand just how significant this was, scientists realized that the muon produced by this neutrino had an energy of 120 PeV peta-electron volts, about 100 trillion times more powerful than visible light photons. But here's where it gets even more mind. The neutrino, responsible for this burst of radiation, must have had an energy of 220 PeV, which is 22 times greater than the previously highest recorded neutrino. This was already beyond anything we had ever encountered before, but that was only the beginning. The trajectory of the neutrino also raised some questions. What made this discovery even more intriguing was the path this neutrino appeared to have taken. When scientists reconstructed the trajectory of the neutrino, they found something unusual. It was moving almost perfectly horizontally across the Earth. This suggested that the neutrino had traveled a long distance, not just through the upper atmosphere, but through significant amounts of water and rock, possibly all the way from deep space. The neutrino passed through the Mediterranean Sea, traveling through layers of Mediterranean rock before interacting with the KM3 net detector, producing a muon, and emitting the burst of light that was so powerfully detected. This path was crucial because it ruled out the idea that the neutrino came from the upper atmosphere or was the result of a cosmic ray. These types of particles are usually absorbed much quicker and would not have the same path or impact. This neutrino seemed to have originated from deep space, and the most plausible source was thought to be powerful cosmic objects like quasars or blazars. These objects are known to be extraordinary sources of radiation and energetic particles. Quasars, in particular, are known to be extremely distant, extremely powerful. Supermassive black holes at the centers of galaxies that emit jets of high-energy particles, including neutrinos. Blazars are another type of active galaxy that emits intense radiation. Based on the high energy of this neutrino, many scientists initially believed it must have come from one of these sources. However, as researchers traced the neutrino's trajectory, they found something baffling. There was no known astronomical object at the location where the neutrino appeared to have originated. There was no quasar, blazar, or any other known powerful source in that region of space that could explain such a high-energy neutrino. This left scientists stumped. If this powerful particle came from deep space, then why couldn't they find its source? Why was there nothing in the trajectory's path? This raised the stakes of the mystery, as it appeared to defy the usual expectations for powerful neutrino sources. Normally, when similar energetic neutrinos are detected, scientists can trace them back to one of these known cosmic accelerators. But in this case, that process didn't work, making this event one of the biggest astrophysical mysteries of recent years. As the search for an explanation continued, scientists considered several possible sources for this unprecedented neutrino. One of the first ideas explored was the concept of a cosmogenic neutrino, which arises from interactions between ultra-powerful cosmic rays and background light in the universe. These interactions are extremely rare and require specific conditions to occur. However, given how unlikely this explanation seemed, it did not fully satisfy the scientists. Furthermore, there was another issue with this cosmogenic neutrino theory: sensitivity. KM3 while advanced, is not as sensitive as the IceCube Neutrino Observatory in Antarctica. IceCube has a much higher chance of detecting such a high-energy neutrino, especially one as powerful as the one recorded. So, if this neutrino were a result of a cosmogenic event, why didn't IceCube see anything similar? Statistically speaking, IceCube should have detected a similar neutrino, but it didn't. This discrepancy led scientists to think there might be another, more exotic explanation. The puzzle deepened when a group of scientists, led by Alexander Klipfel and David Kaiser, proposed a more radical hypothesis. What if the neutrino burst was not the result of an ordinary cosmic ray interaction, but instead was linked to something even more exotic, an evaporating primordial black hole? This theory, though speculative, was based on the long-held but still hypothetical idea that primordial black holes could exist. These tiny black holes are thought to have formed in the early universe, possibly just moments after the Big Bang, and they would have properties very different from the supermassive black holes that we typically observe today. Stephen Hawking, the renowned physicist, famously proposed that black holes could evaporate over time due to a process known as Hawking radiation. Hawking radiation suggests that black holes are not entirely black, but emit radiation as they slowly lose mass. The process accelerates as the black hole gets smaller, leading to an explosion when the black hole reaches a critical size. This explosion could release an enormous amount of energy in a very short burst, just the kind of phenomenon that could produce a powerful neutrino like the one detected by KM3 according to this hypothesis. The burst of neutrinos observed on February 13, 2023, could have been the result of a primordial black hole nearing the end of its evaporation process. As it evaporates, it would release a flood of radiation, including neutrinos, in a final burst of energy. This explosion could have been so powerful that it was detected by KM3 but not by EC, because the event occurred relatively close to Earth within the solar system itself. The proposal that an evaporating primordial black hole could have caused the neutrino event raised a host of new questions. Primordial black holes, while still hypothetical, are fascinating objects that could have formed. Right after the Big Bang, these small black holes would have different properties compared to the supermassive black holes that we typically observe at the centers of galaxies. If they do exist, primordial black holes would be incredibly small and would slowly lose mass over time due to Hawking radiation. As the black hole loses mass, the radiation it emits would become increasingly intense. When the black hole reaches a critical size, it would suddenly evaporate in a massive burst of energy, creating a signature of high-energy particles including neutrinos. This burst of energy would be brief but extremely powerful, producing a bright flash of radiation that could potentially be detected by neutrino observatories like KM3 The timing of the neutrino event in 2023 made this hypothesis even more intriguing. If the event was indeed caused by the evaporation of a primordial black hole, then it would have to have happened very close to Earth within our own solar system. Specifically, it would have needed to be within 2,000 astronomical units, which is within the outermost boundary of the solar system, known as the Oort cloud. This proximity would explain why KM3 detected the neutrino, but IceCube, located in Antarctica, did not. If the event came from outside the solar system, it would have been detectable by both detectors, as the signal would have been much more diffuse and would have reached both facilities with similar intensity. But if the source was much closer to Earth, it could explain why only one detector picked up the signal and why the energy was so concentrated. This theory presents a tantalizing possibility that the neutrino event was the first ever observed burst of Hawking radiation, marking the death throes of a primordial black hole. If this is correct, it would be a revolutionary discovery. Not only would it confirm the existence of primordial black holes, something that has remained a hypothesis for decades, but it would also provide direct evidence for Hawking radiation, a concept first proposed by the legendary physicist Stephen Hawking. In 1974, if the neutrino burst was indeed caused by the evaporation of a primordial black hole, the implications for science could be profound. This discovery would represent a major breakthrough in our understanding of black holes and the nature of the universe itself. The detection of Hawking radiation, an effect that has been theorized for decades but never observed, would confirm one of the most exciting predictions in modern theoretical physics. Primordial black holes, if they exist, could provide crucial insights into the early universe. These objects would have formed just moments after the Big Bang, potentially shedding light on the conditions that existed in the very early stages of the cosmos. Their existence could also help explain some of the missing matter in the universe, as they might constitute a portion of what is known as dark matter, the mysterious substance that makes up a significant portion of the universe's mass, but has yet to be directly detected. Moreover, the idea that a primordial black hole could be hiding within our own solar system adds an entirely new layer of intrigue. The Oort cloud, the distant region of icy bodies at the edge of the solar system, could be home to these elusive objects. If primordial black holes do reside there, they could be influencing the motion of objects in the Oort cloud and even affecting the dynamics of the solar system in ways that we have yet to fully understand. This also opens up the possibility that there are more such objects yet to be discovered. The potential for detecting more primordial black holes in the future is exciting, especially in light of new advancements in neutrino detectors. As we mentioned, KM3 is being upgraded, and the new version will have improved capabilities for pinpointing the exact direction of incoming neutrinos. If another neutrino burst like the one detected in 2023 is observed, scientists will be able to trace its origin with far greater precision, helping to confirm whether it came from a primordial black hole or another, still mysterious source. In fact, recent studies suggest that there is a 90% chance that we will observe more primordial black holes within the next 14 years, particularly if they are located within the solar system. This means that the 2023 event could be just the beginning of a new era of discovery in astrophysics. The potential to detect these objects and even harness the energy they produce is revolutionary. If we could learn to extract energy from primordial black holes, it could lead to breakthroughs in energy generation, potentially offering a virtually unlimited source of power. Additionally, the detection of such an event raises new questions about the nature of dark matter and its role in the formation of galaxies and stars. If primordial black holes contribute to dark matter, understanding their properties and behavior could give us new insights into the most fundamental aspects of the universe. While this remains a fascinating hypothesis, one that has yet to be fully confirmed, the possibilities are immense. The mystery surrounding the neutrino burst of 2023 has opened up numerous avenues of exploration and has given us a glimpse into the unknown. Whether the event was caused by a primordial black hole, a cosmic accelerator, or something else entirely, it has left us with more questions than answers, and that's what makes it so exciting. As the research continues, we'll likely uncover more data and clues that will either support or challenge the idea of evaporating primordial black holes. But for now, we're left with a tantalizing mystery, one that may very well redefine how we understand the universe and its most enigmatic objects.